Started recording.
So ninguém nem eu vendo a vaca. So como enteringe vendo. Eso não? O grupo está dele. Eti aso kirangira entari. Ecco, musiro mwacho. Mwana semeye kwa musiro mwacho. Yes, hello.
Hello.
I want to continue from where Sylvester stopped. And I think other members will find us along the way. Mr. Sylvester stopped on the invariant formula. That is where I will begin. It is very necessary that you get to know what this one means. First of all, the invariant point, an invariant point, the notes are not talking about it, but a point is said to be invariant. A point is said to be invariant if it remains in its position after a rotation or a translation. An operation has been done to it if it remains in the same position. If it remains in the same position, that point is going to be invariant. So we want to see a formula we can use for such points for which when you reflect it, when you rotate it, when you translate it, it remains in its position. We want to see how you can differentiate such a function of comprising of those points. And now those points, they are polygons that can be made of those points. How to differentiate such a function if it is a function of the kth form? We can find the derivatives of the kth form of that function. And now let this function comprise of, let it have fields v1 up to vk. So we want to differentiate to find the derivative of this function. Let us refer to it as the want to refer to it as the omega of the fields v1 up to vk. Now we want to differentiate the pairs of these points from k, from the kth pair to k plus 1 pair of an arbitrary curve, smooth curve of the vector v1 up to vk. So the derivative of this curve is actually the summation. Is actually the summation of the negative index. That is why you are seeing -1 is the summation of the negative index of the power, or of the power I minus 1 into the field, the respective field. That is why we are calling it the ith field, for which it carries the pairs V1, V2 up to any other V. Let's call it Vn. Plus it is the summation. So plus I want to take into considerations the powers of -1. In the first pair or in the first set, we have a power of I minus 1 into V. In the second pair or in the second summation, we have the power J plus K. Now J plus K, it is a row and a column. It is a vector field, that is I and J. So you have to look at those powers and distinguish them very well. Now, I want to define omega V, because you may ask what omega V is. I want to define omega V. Omega V is a set of these vectors from V1 up to Vk. From V1 up to Vk, you can see this formula is a set of these vectors from V1, V2 up to Vk, up to Vk. Let's look at an example. Let's look at an example. Consider sigma is equal to u dx1 cross dx2. Now, these powers are coming from the summation.
Okay.
Vianney, you have a question? Vianney, you have a question? Vianney, you have a question? Sister Prudence, you have a question? Because I hear you talking.
Yes. I'm following Wilberforce.
Okay, please. So I want us to look at this example where we are considering what's this? Where we are considering this function of u dx1 cross dx2. Those are the powers that are coming from this formula. So over a one-form basis, I hope you still remember what a basis is. Somebody can mute the microphone. Over a one-form basis, somebody mute your microphone. Somebody mute your microphone. Yes. So we want to consider the derivative of that function, and we want to find its exterior derivative. So we are differentiating this function. You differentiate both sides, and you differentiate the other side. So the derivative will come on the variables. That's why you say du cross dx1 cross dx2. dx2. So we want to we are differentiating both sides. So u, the derivative of u is actually the summation. We are substituting this formula. Is the summation, this summation. So that is why we just insert it there. Then we cross d1, dx1, dx2. Putting the summation outside. So you can see that this formula just remains the same. You're just putting the summation, and you are summing from I is equal to 3 to I is equal to n. Why are we summing from that? Why are we summing that? Because we have I is defined from 0, 1, 2, 3, but we have a function of two variables, and therefore we begin from the third one. you realize that when I cross Sylvester, when I cross the x1, the xi with the xi, it is the same direction. When I cross them, remember cross product is a sign. It means the angle between them is 0. So this function will reduce to 0. This function will reduce to 0. And therefore, I make the substitution where I find that. I'll make a substitution of 0. I'll make a substitution of 0. So I continue with my derivative. Because now, because you can see, you can see, I want to bring this item out. You can see that I have the x. How can I highlight it? So I wanted to highlight the formula, but it looks like it cannot be highlighted. But I hope you see the formula that I'm considering. That we have the x high to the x to power I cross the x to power 1. That is also the x to power I. When we cross this, we are saying that down here, we are saying that it is the formula reduces to 0. So that's why we have. That's why you have a cross product of this all function is equal to 0. So what does this mean? It means the all integral, I mean the all derivative of this function is reducing to 0. The all derivative of that function is reducing to 0. Example number 2, exactly the same as example number 1. So we have for a one-form equation or function of that form in 2 dimensions, that is, it has 2 variables, x and y. We can apply the above formula. That is when in this question we are going to consider where we have x1 is equal to x and where we have x squared, we are going to take it as y. So we apply the summation. We apply this summation. We apply this summation. So we apply this summation. We apply the summation. We differentiate both sides. We apply the summation on dx, and we differentiate the other side. We also apply the summation on v. So expand this using the same summation. So you will make sure that you refer to the original formula, because this is what applies. And whenever you find a cross product in one direction, you just put that to 0. You just put that to 0. For example, where you see dy cross dy, this will be put to 0. And also where you see dx cross dx, the same direction. The same direction. Remember the cross product formula, which is multiplied by sine of the angle. So if it is the same direction, it will imply that that angle is 0 and sine of 0 is 0. So you remain with these components without cross products in the same direction. So we have this, and also remain with this. Hope you can follow that. We pull out the same the common term. We pull out the common term, and this formula reduces to this. So with this, I will move to the Lambert operator. The Lambert operator. We'll move to the Lambert operator. Now, this is actually an application of the invariant formula But who are not doing physics, I think you'll find problems here. Anyway, let me try my best. But it is an application of the physics. That's why you see, as the notes indicate, that electromagnet in resistive relativity, electromagnetism, and wave theory. So this is applied, actually, it is a physics concept. However, we can apply the invariant formula. Let's do so. So let's say the operator is named. Okay, that is a theory. So the D'Alembert formula is actually sometimes called the wave operator or the Laplace. Sometimes it's called the wave operator, which is sometimes called the Laplace operator, named after the founders of the formula. It is represented by this box. Well, I want to select the box, but I hope you can see how I've highlighted it. That is its representation. So it is represented by this box facing in a respective direction. And what does this say? I'll go straight to this last formula, that it is the second derivative with respect to a variable, which in most cases is t, is the second derivative of the variable, which is in most cases t, times the inverse, of the surface. Let me call it c squared, then minus the operator, minus this operator. Let me repeat it. It is the second derivative with respect to time of the function given times the square of the inverse of the surface C, then minus the operator there. An application of this, these are usually physics applications. An application, if you're interested in the application, I can refer you to electricity and magnetism and the classical 2, the people of physics. As I'm winding up to invite Madam Shakira, okay, Mr. Sylvester, let me also talk about the Green's theorem. The Green's function. The Green's function, which we are representing as G into or G of x minus x prime. For the Lambert's theorem, or for the Lambertian, what we mean for the above formula is defined by this equation. So the Green's theorem is defined by this. So what does this mean? We get the changes times this element x minus x prime. X minus x prime. It would be better if we illustrate it with an example. Let me see if we can have an example here. Oh, there's no example. There's no example here. Okay, let me just go to the double integrals. The double integral. Now, one thing you have to know is that a single integral is an area. A single integral is an area. So I think you'll find no problem in understanding that a double integral is a volume. A double integral is a volume. So if you're asked to calculate the volume, probably you have to use a double integral. I mean a volume of some bit of complicated figure, because if it is a volume of rotation, then a single integral can work. But a volume of a solid figure, a volume of a solid figure, say a volume of a cylinder, then you have to use a double integral. And a double integral of a volume of say a figure of this nature, kind of a cylinder, which is defined by a curve. Each volume can be defined by using the double integral. I think this one brings it proper. This one brings it proper. So you'll have the limits. Our double integral, if it is in dimension x and y, we are taking the third component, z to be 0. So we are differentiating first with respect to x. So we differentiate this function with respect to x. And again, after getting the answer, you differentiate with respect to y. You differentiate with respect to y. I hope you understand this. I am looking for an example to illustrate this. An example. Oh, well, the lecturer did not put examples here, but I hope you can find an example. What I want to stress is that it is the volume. You first differentiate with the first identity, say differentiate with the y, and then you differentiate the answer with the x. I hope you find it useful. The Jacobian matrix, Mr. Sylvester is going to begin from here. Yes, Mr. Sylvester, you're welcome.
I'm back in action. This is going to be interesting, as you can see. I'm going to just read through this so that the things can stick into your heads. And when you're in the paper, you'll be able to recall my voice. So the Jacobian matrix, that's where I'm starting from. And my colleague Shakira will begin from Jacobian determinant. So now let's see this. The Jacobian of a function describes the orientation of a tangent plane to the function of a given point. You are telling me last time that I was speedy. Okay, let me try to reduce on this speed so that you can all be able to get me well. So in this way, the Jacobian generalizes the gradient of a scalar valued function of multiple variables, which itself generalizes the derivative of a scalar valued function of a scalar. Likewise, the Jacobian can be thought of as a describing amount of stretching that a transformation imposes. For example, if we have x2 and y2, this can be equal to f of x1, y1, and it can be used to transform an image. So the Jacobian of f can be given as j of x1, y1, and this describes how much the image in the neighborhood of x1, y1 is stretched in the xy direction. Are we all together? If a function is differentiable at a point, okay, this is something like a node. If a function is differentiable at a point, its derivative is given in coordinates by the Jacobian, but a function does not need to be differentiable for the Jacobian to be defined. We need to get this point very clearly. Since only the partial derivatives are required to exist, are we all together? So the importance of a Jacobian lies in the fact that it represents the best linear approximation to a differentiable function near a point. In this sense, the Jacobian is the derivative of a multivariate function. Are we all together? Take note of this. The Jacobian is the derivative of a multivariate function. Are we all together? So let's go to another thing here. So if a point, if P is a point R, if P is a point in R, real numbers. P is a point R in R, and F is differentiable at point P, then its derivative is given by JF of P. In this case, the linear map described by JFP is the best linear approximation of F near the point P, in the sense that f of x equals to f of p plus jf p of x minus p plus the norm, that is the distance between p and x. Now for x close to p and where O is the little o notation for x to p, and the norm x minus p is the distance between what? Between x and p. So in a sense, both the gradient and the Jacobian are first derivatives. Sefma, are you with me? Sefma is open. Okay, let's continue. We have said here, in a sense, both the gradient and the Jacobian are first what? First derivatives. The former of the first derivative is scalar function of several variables. The latter first derivative of vector functions of several variables. In general, the gradient can be regarded as a special version of what? Jacobian. It is the Jacobian of a scalar function of what? Several variables. The Jacobian of the gradient has a special name, that is the Hessian matrix. Not Asian, but Hessian. Hessian matrix, which in a sense is the second derivative of a scalar function of what? Of several variables. So we shall go to the inverse of a Jacobian. According to the inverse function theorem, the matrix inverse of the Jacobian matrix of an invertible function is the Jacobian matrix of the inversible function. That is to say, for some function f that is mapped on Rn to Rn, and the point P in that Rn is given by this. The inverse is given by that formula you're seeing there, Jf prime. As you can see there, it follows that the scalar inverse of the Jacobian matrix of a transformation is the Jacobian determinant of the what? Of the inverse transformation. So you can see those things there down are the uses of that Jacobian. Have the dynamical systems, have the Newton's method. You can read through them, be able to master them. So I think my colleague start from here. Hope you'll be able to recall my voice when you're in the paper, because it has been a nice one. Shakira, you're welcome.
Thank you, Mr. Silva. Thank you, Mr. Silva. Thank you, Mr. Silva. I'm going to talk about the Jacobian determinant. Here they're saying if M is equal to n, then f is a function from n space to n space, and the Jacobian matrix is a square matrix. We can then form its determinant, known as Jacobian determinant, and this one is sometimes called the Jacobian. The Jacobian determinant at a given point gives important information about the behavior of f near that point. For instance, the continuously differentiable function f is invertible near a point P in Rn. You'll go through this. Here there is an important point to note. The absolute value of the Jacobian determinant at P gives us the factor by which the function f expands or shrinks volume near P. This is why it occurs in the general substitution rule. Here they are giving us the use of the Jacobian determinant. The Jacobian determinant is used when making the change of variables, when evaluating a multiple integral of a function over a region within its domain. Let me go through the examples. For example 1, they are saying the transformation from spherical coordinates, that's r, theta, and phi, to Cartesian coordinates x1, x2, x3 is given by the function. The function is given with components x1 equals to r sin theta cos theta. Then x2 is given as r sin theta sin phi. Then x3 is r cos theta. When finding the Jacobian matrix, we have to look for the partial derivatives of our x1, x2, x3 in terms of theta, phi, and r. So here they are showing the Jacobian matrix. When getting it, let's for the first column, we are going to find the partial derivatives of x1, x2, and x3 with respect to r. Then for the second column, we are going to find the partial derivatives of x1, 2, and 3 with respect to alpha, to theta. Then for the last column, we shall find the partial derivatives with respect to phi. And when you find them, here they are showing us the matrix we get after getting the partial derivatives of all that. And it's a square matrix. As you see, it's a 3 by 3 matrix. And when you use from our linear algebra 1, when you go through those methods of finding the determinant, we finally get r squared sin theta. Here they are saying, as an example, since dv is equal to dx1, dx2, dx3, this determinant implies that the differential volume element dv is equal to r squared sin theta, dr, the alpha, the theta, the phi. The phi, there is a box, but it's the phi when you follow the steps we have been using. Nevertheless, this determinant varies with coordinates. To avoid any variation, the new coordinates can be defined as w1 equals to r cubed over 3, w2 negative cos theta, then w3 is phi. Now the determinant equals to 1 and volume element becomes r squared, the r sin theta, the theta, then the phi. Now this w1 you can see from our upper determinant, r squared sin theta. When we make our r to be r cubed over 3, we can see that r cubed over 3, when we differentiate it, we go back to r squared. And when we differentiate the negative cos theta, we get our sign in the upper determinant. Then the w3, which is equal to phi, when we differentiate the phi, we get a 0. That's why in the determinant, we don't have any value in terms of phi. So here they're saying the volume element becomes r squared dr. That means in our determinant for r, it's in terms of the r, then sine theta, the theta, then the phi will be equal to the W1, the W2, and the W times the W3. Let's go to example 2. Example 2 says the Jacobian matrix of function from R3 to R4 with components y1, y2, y3, and y4. Using the idea we have seen above, we can see that when finding the Jacobian matrix, we are going to find the partial derivatives of x1, x2, and x3 of y1, y2, and y3. That's from this step, they are showing that when finding the Jacobian matrix, we are going to find the partial derivatives of the first column will be of y1, y2, y3, and y4 with respect to x1. Then the second column, it will be with respect to x2, and the third one will be with respect to x3. And we are getting our Jacobian matrix. You can go through it and confirm. This example, it shows that the Jacobian need not to be a square matrix. Here we are seeing that it's a 3x4 matrix. Then example 3, is that you follow the same steps, you get the Jacobian matrix. Then after getting the Jacobian matrix, it's shown you use our methods of finding the determinant, and here they got R as our determinant. And for this example 3, it shows how the integral in the Cartesian coordinate system is transformed into an integral in the polar coordinate system. The double integral of f of a y over the region of a in the xy plane is equal to the double integral of f of xy over the region b in the xy plane. Members, I think you're following. Are you following?
Yes, you can continue.
Then for example 4, there is nothing different from the upper examples. There is nothing different from the examples we have seen above. You follow the same steps here they're showing. You get the Jacobian matrix. After you do that, you use the same methods of finding the determinants, and you get your determinant. From this example 4, they are telling us that from this, we see that f reverses orientation near those points where x1 and x2 in our functions have the same sign. The function is locally invertible everywhere except near points where x1 is equal to 0 or x2 is equal to 0. Members, to be on a safer side, you have to follow the steps we have been going through and try out this assignment. In case of anything or anywhere get stuck, you can contact me for more clarification. Thank you.
Contact Sylvester also. Hey guys, have a nice time. I think
So members, we want to conclude. We have presented for the rest of the group. For the rest of the group, they were around, but we decided to choose a few because the content was much and the time was very little. So we presented for the rest of the group. Thank you. We are going to, I think we'll send you this work if in case you need it. Thank you.